Afternoon, everybody. Can you hear me okay?
Yeah.
Okay. All right, I guess I'd say a little bit about the payload that I have. We were flying a payload on SpaceX whenever it launches. It's a payload, we call it Self-Assembly in Biology and the Origin of Life. So it's a rather ambitious name, but it's what we're doing is growing protein fibers in orbit, and the fibers that we're growing, if you look at the neurons and the brain of people who have died from Alzheimer's disease or various other neurodegenerative diseases, they form these protein. That's interesting.
This is only a test.
A loud spark behind me. So anyhow, in the neuron cells, both the intercellular fluid and the extracellular fluid, there are fibrous proteins they're called amyloid plaques. So they form these plaques, and I've been studying them in the laboratory at Florida Tech for about a decade now to try and understand how they grow. There are many different types of proteins, but they all grow these fibers in more or less the same process. And so we've been studying that, trying to understand the process itself. And we have devised a small experiment in a NanoRack module that's going to fly, and we will grow protein fibers in orbit for a period of 30 days. And we're trying to understand the formation process, so we need a time series. It takes them roughly 20-25 days to go from a solution of proteins in a buffer solution to long, thin fibers. The fibers are about one protein in diameter and can be as long as 15 or 20 microns. So they're nanometers in diameter and 15 or 20 microns long. And so it's a very interesting self-assembly process where spontaneously fibers form out of a solution. We need to have a time series. In the laboratory, that's easy, because we just start the incubation process and we sample it every few days, and we sample the fluid, and the only way we can measure the fibers is with an atomic force microscope, which can get down to nanometers resolution, so we can measure the fibers themselves. In orbit, we can't do that. First of all, we don't have an atomic force microscope on the space station, and it's fairly crew intensive to do that. And so we've designed a small automated laboratory the size of a NanoRack module, and we have 9 vials on there. And in order to start the incubation process, you have to mix the protein powder with a buffer solution, and they have to be held separate until you want to start the process. And so we have a vial that's a specially designed vial that keeps the powder separated from the buffer solution until we want to start the incubation process. We also have to raise the temperature to 50 degrees Celsius, and so the vials have a heater foils wrapped around them and a control circuit to control the temperature. And so in orbit, we will activate one vial and let it grow for 3 days. We'll activate one and let it grow for 6 days, etc. So we do that in parallel. And when we get the 9 vials back, we'll have one that's been activated for 3 days, one's activated for 6 days, and the process stops when we bring the temperature back down to ambient temperature. So we'll have this time series. It will be delivered back to us in the lab, and we will measure the proteins. And we're hoping to see, we're not sure what we're going to see really. One thing is we should form more complex structures, because in the lab, the proteins themselves they settle gravitationally to the bottom of the tube and form these fibrous mats where they're just individual fibers falling all over each other like that. The protein fibers form, before they do that, they form complex structures where long fibers will wrap around each other in helical formation, and they merge together and come apart. And we presume that in orbit, in weightlessness, the fibers will not settle gravitationally, and so we'll be able to form more complex structures, maybe triple fibers, quadruple fibers. We're really not quite sure. So that's the experiment, and we were looking forward to flying tomorrow, but we'll wait until it's right. The time is right.
There you go.
So that's